Hello everyone. Today we're going to be talking about our progress on the final project for EECS 106B. Our project specifically focuses on RRT motion planning for the hexbug beetle. So without further ado, let's get into it. So yeah, my name is Sagar. I'm a senior studying computer science and math.
My name
I'm
is Kaichin.
Kunal, sorry, go ahead.
Oh, my name is Kaichin. I'm senior studying electrical engineering and computer sciences.
I'm Kunal, senior studying CS in the LNS department.
And so our research question is really focused around how effective is RRT-based motion planning with visual motion tracking for a severely underactuated system. And the system of choice, as we'll get to, is a hexbug beetle. And we also want to research into how effective is CV tracking of a moving object, and can this CV tracking be used for system identification and trajectory planning? So the main motivation for our work is extreme scenarios of mechatronic systems involving critical hardware or software failures, right? So consider the extreme case of aileron failure on a plane or a steering assembly failure in a self-driving car. Critical hardware failures on autonomous systems severely limit the control input space and cause the system to be underactuated. In these sort of emergency situations, a unique motion planning method is needed that can handle the limited range of motion commands. And so our real challenge is when we're given these sort of highly underactuated systems, what is the best way for us to go about designing a motion planner? And the test subject of choice that we've decided to use to simulate these sort of highly underactuated systems is the hexbug beetle. The hexbug beetle is, we thought it would be a very powerful exploration and mapping robot for small spaces unreachable by larger mobile robot platforms. Right? It's really a $20 robotic toy. It's designed for kids at the end of the day. But it does kind of have some unique limitations, and that can only move in two ways. So to characterize the motion of the hexbug, we can think of it as using these two sort of motion primitives. Right? The first motion primitive is to drive forward at some constant velocity. Right? Note that this so-called driving forward is actually slightly imperfect in that the robot will tend to drift as it goes forward, and so that's just something that is imperfect about how the robot was manufactured, and so we'll need to kind of correct for that in our or account for that in our motion planning. Right, and then the other sort of motion primitive we can think about is that when the robot comes in contact with some obstacles, or if it hears some auditory like sound input such as a hand clap, it'll execute a turn, right, in sort of the shape of a J, while reversing. Right, and what's important to note about the system is that it's highly underactuated. Recall that underactuated control systems are those in which control inputs cannot accelerate the state of the robot in arbitrary directions. Right, in this case, not only can we not accelerate the robot in arbitrary directions, but even just control over the linear velocity it cannot really be modulated. Right, the robot has to continue at a fixed pace without any sort of direct control over the linear speed. And in addition, the steering angle can only be commanded by this sort of one primitive, right, where we provide some sound input and the robot performs this turn. Right, and because of this, the robot is highly underactuated system, and this is what really forms the challenge in motion planning for the system. So some related work on this. There's actually relatively little. We couldn't find any papers regarding motion planning for the hexbug beetles in particular. We did find some papers that were relevant for some of the other hexbug bots, but none on like the one we're working on specifically. right? There was some research relating to RRT planning for small under-actuated bots, and in general, I think RRT with the rapidly exploring random tree does seem to be a popular uh, planning algorithm for situations like these when we have sort of very well-defined motion primitives on what is possible for the robot to do, right? And we also have a sort of broad sample space. And there's also one of the other tasks, as we mentioned, is the sort of computer vision tracking of our robot. And there's a lot of literature around key point detection or key point identification and tracking using computer vision. And we even found one relevant paper that uses vision for simultaneous key point discovery and system identification. And so it's somewhat similar to what we hope to do with our modeling and control for the hex bugs.
So how do we approach this from a hardware to system design perspective? We've so far determined our hardware system to perform experimental validation of other components of our research. You can see a system diagram of how we plan to approach our experimentation and research to the right. Our system composes of a control sensing method, which is computer vision motion tracking, provided from USB or built-in webcam on a Baxter or Sawyer robot, where the arm will view the hexbug movement happening on a lab table. We will set up an environment for the hexbug to motion plan it on the table. And a speaker will be attached to the lab PC, which serves as our control input to the hexbug, which will respond to the sounds played from the speaker. For our camera motion tracking, we plan to use OpenCV to track hexbug behavior over time and perform online control. We will probably use frame deltas to detect the moving hexbug, use position data to fit motion primitives and correct for noise. And for the final implementation, control will use online motion tracking and perform online control and use these position datum as a feedback term. The next steps we will be working on throughout this project as the weeks go on are comprised of 3 steps. First, we need to perform system identification to create realistic models of the motion primitives the hexbug has given experimental data. Secondly, we'll need to read more on motion planning theory and design a motion planner based on RRT using the speaker to give commands. And lastly, we need to run experiments by running the motion planning system we've developed on the actual hardware and adjust based on the performance. For a deep dive on the system identification initial plan is that we will work on identifying the robot's key 2 motion primitives using computer vision. Our initial plan for the system ID is to collect consecutive finite difference velocity vectors calculated from the frame deltas we collect from the USB cams in groups of some constant m amount, then execute k-means or other clustering on the data with k equals 2. We can also use classification methods if k-means fails. Using these clusters, we can identify the drift angle, radius of curvature of turns, and constraints on the position that the hexbug has that is not immediately apparent from the manual. Then we will look at motion planning.
Yeah, so when the robot's antenna, as the hexbug, as shown before, it'll execute the same reversing J-turn as if the sound clap was played. So that kind of behavior needs to be accounted for, as sometimes in the case of when turning into like a tight corner when there's a lot of obstacles, it could be more optimal to actually hit the obstacle rather than play the sound clap, as the sound clap control, as we mentioned before, it's not modulated and the turns are at a fixed angle and speed, as shown in that video. So that's kind of how the motion of the robot would work. In depth, because the steering system it's not accurate and the robot's forward movement has drift, we plan on implementing robust trajectory cost functions to account for that. So, that would incentivize the robot to choose RRT nodes that it can most likely reach. And then our stretch goal is to perturb trajectories and model path permutations as Gaussian processes, which will hopefully increase the accuracy of our model and account for how underactuated our system is. And learning opportunities and challenges from completing this project is that with only 2 motion primitives, RRT would need to be tuned a lot, which means we would need to have like a pretty high number of experiments and actually observe how it behaves, and have to write cost functions to see if we can smooth out trajectories. We need to find creative ways to bounce the robot off of obstacles, as we previously mentioned, and model that behavior as such, and then have system identification approaches and then prototype the vision-based feedback mechanisms. So overall, a lot of experimentation and a lot of tuning will need to go into this project, and especially to reach our goals. But yeah, overall, that kind of summarizes our project, and we encourage, definitely would love to hear feedback, as it would be very helpful for us as we actually implement this, and hopefully can make it as easy and effective as possible. Thank you.